All right, welcome back, everybody. So, chapter 13, my most favorite chapter. Now, you may be thinking to yourself, trigonometry, isn't that just triangles and stuff? The answer to that is kinda. Now, let's talk about that. You're like, well, wait a second, I only see triangles. What's going on here? This is algebra. This is not geometry. What are you doing to us? Here's what I will say. We are going to do everything you've learned about trigonometry. We're going to talk about today. You've learned right triangle trigonometry. You guys remember SOHCAHTOA?
No.
SOHCAHTOA? Sine, cosine, tangent? That's what we're going to learn. That's what we're going to talk about today. Beyond today, it should be all brand new stuff. Except for, did you guys do law of sines and law of cosines? I don't know. Ring a bell?
Yeah.
Maybe, maybe not. So maybe it's all going to be new. Okay? All right, so let's talk about right triangle trigonometry. Trigonometry is a topic that can be used in a variety of different math classes. Like some people take trig itself. Like sometimes trigonometry is taught as its own subject in high school. Or maybe you get to college and you have to take a trigonometry course. It's not geometry. It's not algebra. It's not calculus. It's its own thing. It's its own separate field of mathematics. It's trigonometry. Now, trigonometry allows you to solve for different pieces and parts of not only triangles, but also, and not only right triangles, but all sorts of triangles. And you can pretty much, if you're talking about any sort of distance, like if you're out in a field and you want to find the distance to this point or the distance to this point or the distance in between those 2 points, if you've got two other points in space that you're trying to find either the distance there, or the distance between them, you can use trigonometry to find any distance that you need and any angle at which you have to travel. So a lot of trigonometry can be used in, aviation and, any type of travel or anything like that. It can be used a lot in a lot of different areas. It can be used in a lot of different things. So what we're going to do here is we're going to start small. We're going to start talking about how does it apply to a right triangle. And then we're going to make it grow and we're going to say, okay, how does it apply to any type of triangle? And then we're going to say, okay, how does it apply to anything else? How can we create triangles so that we can use trigonometry with them? So first things first here, we're going to talk about sine, cosine, and tangent. Now, what is a trigonometric function? And that's how we say that, trigonometric. What is a trigonometric function? A trigonometric function is a function whose rule is given by a trigonometric ratio. Very stupid definition again. A trigonometric function is a function whose rule is given by a trigonometric ratio. Well, what is a trigonometric ratio then? Well, yeah, I know, I'm saying that a lot, right? It's either sine, cosine, or tangent, or their inverses. Basically, that's it. There's three trigonometric ratios, sine, cosine, or tangent. But you also have their inverses as well. A trigonometric ratio compares the lengths of sides of a right triangle. That's basically what sine, cosine, and tangent are. People always ask me, what's that sin thing on my calculator? That's just a ratio, a comparison of two sides of any triangle. Usually we're talking about right triangles. Cosine is just a comparison of two sides. Tangent is a comparison of two sides. Now, sine, cosine, and tangent are always used in reference to an angle. Now, that angle that we are referencing is an angle called theta. It's, you know how we normally say in algebra land, if we got a missing number or we got a missing piece, we usually call it x? Yeah, not anymore. In trigonometry land, you say, well, if I've got a missing angle measure, we're going to use the Greek letter theta. Oh my God, theta. We're going to use the Greek letter theta. Now, theta, it's just a letter of the Greek alphabet, and it looks like this. Just a circle with a horizontal line through it. And no, it's not this. That's a zero.
I don't see
Oh, I should
difference.
use it with an angle.
It's a
Horizontal line, not a slash through it. It's not this, that's no solution. It's not that, that's 0. It's a circle with a horizontal line through it. That's theta.
So if I accidentally on the test, I like angle it.
No, I don't care. Whatever. Just as long as you know what you're talking about. Just as long as you know what you're writing. The Greek letter theta is traditionally used to represent the measure of an acute angle in a right triangle. The values of a trigonometric ratio depend on the angle. They always depend on theta. Theta is extremely important. The angle at which you're talking about, the angle at which you're referencing, is going to be very, very, very important. Okay? Because the ratios will change depending upon the theta that you're working with. Now, let's talk about that sine, cosine, and tangent. If you don't remember it, it might be a good idea to write it down. I figured you guys would know it by this. SOHCAHTOA. That is an acronym. That is is that called like a mnemonic device? It's a way to remember sine, cosine, and tangent using the first letters of each thing. Okay, using the first letters of each thing. Like Holmes is a way to remember the Great Lakes. Here on Ontario, Michigan, Erie, Superior. That's one word.
What are you talking about?
Never heard of that?
No.
Holmes, Homes, a way to remember the Great Lakes. Huron, Ontario, Michigan, Erie, Superior. Holmes. It's a way to remember. Don't you guys do that for the metric scale? Like kilo, hexadecadecimilli, right? King, Henry, blah blah blah, right? And also, don't you guys remember one? Did you do that in science for like the kingdom phylum class? You guys do ever one of those? Oh, you had a song? Okay, that was.
Don't call it stupid.
Don't offend the song.
It's literally just like
So, SOHCAHTOA is a way to remember the trigonometric ratios and how they relate to each side length. For example, sine is always equivalent to the opposite side divided by the hypotenuse. SOH. CAH. Cosine is always adjacent divided by the hypotenuse, and tangent is always the opposite divided by the adjacent. Now, what does that mean? It always depends on the angle that you're looking at. Like, for example, if I've got a triangle, and I say, and it's a right triangle, and I say this is theta. Sometimes I do write it as a little slanted, I guess. That just happened right there. I didn't even there you go. There's theta. If I'm saying that's my theta, if I'm saying that's the angle that I'm referencing, well then this is the opposite side. This is the adjacent. Remember that word adjacent just means next to. This is the adjacent side, and the hypotenuse is always the side across from the right angle. Right? So sine is equal to the opposite over hypotenuse, cosine is equal to the adjacent over hypotenuse, and tangent is equal to the opposite over adjacent, always dependent upon my theta. Now, what would happen if I change my theta? What would happen if I say, well, now I want my theta not over there, but up here? What if I put theta there? Does my hypotenuse change?
no.
No. My hypotenuse does not change. Does my opposite and adjacent? Yes, now my opposite side is the one down here, and my adjacent side is the one here. Let me ask you a question. What is the sine of this theta? This opposite here, let's call this x and this y. If I call that x and y, what's sine? X, and actually let's, not y. X over h for hypotenuse, right?
Wow.
X over h, opposite over hypotenuse. Let me ask you this. Let's introduce a different variable here, just so we're not talking about theta and theta. Let's use the Greek letter alpha. When you're talking about angles, you usually use Greek letters.
Why do you have to use?
Quiet, please. Quiet, please. Whenever you use angles, and you'll find this through pre-calculus and calculus, you always use Greek letters. So theta, alpha, beta, gamma, whatever. So maybe I introduce another, placeholder here, theta or alpha. Excuse me. If I'm choosing alpha, what is my cosine of alpha?
That would be
Now this turns into my.
X over H.
That's my adjacent now of alpha, right?
X over H.
X over H. So what do you notice about cosine and sine of complementary angles?
Oh, wow.
They're the same. They're exactly the same. And that's one of the things that's a very, very key component here that we have to learn. The sine of any angle is the cosine of its opposite angle. Is the cosine of its complementary angle. Remember, complementary means adds up to 90. Yeah. All right, so let's practice a little bit with it.
Wait.
Yes.
What if you want to find like the cosine of the right angle?
You don't want to do that. And you'll see why when we talk about the unit circle. Okay. Find the value of sine, cosine, and tangent functions for theta. Okay, so do you see how I tucked my theta in the bottom right? Let's find the sine, cosine, and tangent of theta. Well, sine theta is what? 7 over 25. We're just identifying the ratios right now, just to see if you can identify what's going on. Let's talk about cosine theta. What's cosine theta? 24 over 25. And what's tangent theta? 7 over 24. Opposite side divided by adjacent side. Now, did we solve for anything right there? No, we're just identifying which pieces go where, so we're very clear about what's my opposite, what's my adjacent, what's my hypotenuse. Can we identify those things? Let me reinforce this one more time. What if I had called this alpha? What's sine of alpha?
24 over 25.
What's cosine alpha? What's unique about this? What's tangent of alpha? Not the same. The reciprocal.
What?
Because the opposites and adjacents will change, right? One's opposite is the other adjacent. So therefore, when you're talking about tangent, it actually just is the reciprocal of the complementary angle. All right. Let's talk about the special right triangles. Let's talk about the special right triangles. Now, I'm giving you space to write it down below. It's important to know what the special right triangles are. They give it to you like this. I'm going to show you it in a different way. Here's the 30, 60, 90 right triangle. I like to stand it up on its short side, and I like to put in letters. So this is the 30, this is the 60. This is the short angle, that's the big angle. Everything is always based around the short side of a 30, 60, 90 right triangle. If I call the short side of a 30, 60, 90 right triangle x, then the hypotenuse of that 30, 60, 90 is 2 times whatever that thing is. So if the short side is 10, the hypotenuse is 20. If the short side is 7, the hypotenuse is 14. If the short side is 2, the hypotenuse is 4. Now the other leg has a special relationship. Now, here, I'm going to erase this away in a second, but I want to show you why this works. Think about Pythagorean Theorem. If I wanted to find this, let's call it b. I would say x squared plus b squared is equal to 2x squared, right? That's just the Pythagorean theorem. Side squared plus side squared equals hypotenuse squared. So x squared plus b squared is equal to 4x squared when I distribute the two. Distribute the squared. Subtract over the squared. B squared is equal to 3x squared. 4x squared minus 1x squared is 3x squared. And if I go to square root that opposite side, b is actually going to be the square root of 3x squared, which simplifies down into, see the x comes out, x radical 3. And that's that side. X radical 3.
Oh.
It's all based on the Pythagorean. Do you need to memorize? Do you need to know how to do that with Pythagorean? No. I want you to memorize this triangle. That should already be in your brains from last year. But we may need to refresh our memories a little bit. So again, in any 30, 60, 90 right triangle, the base side is x. The 30 side, you're going to hear me reference that, calling it the 30 side. The 30 side is, I'm referencing the side across from the 30-degree angle. That's the 30 side. The 30 side is always what you're looking for. You can use that 30 side to find. So that means also, what happens if my hypotenuse is 50? What's my 30 side? If my hypotenuse is 50, what's my 30 side? 25. We can divide it by 2. Right? If I then know that my 30 side is 25, what's my 60 side?
25.
25 radical 3. Right? 25 radical 3. That number times radical 3. Let's talk about the 45-45. I usually just call it the 45-45. 45, 90, whatever. I like to just put in letters. Now, this is the only isosceles right triangle. So that means that the two side lengths, the two legs of this thing are always equivalent. So if you put x's there, let's figure out what the hypotenuse is using some Pythagorean. X squared plus x squared equals, let's call that c. C squared. Well, x squared at x squared is 2x squared.
Oh.
And then I go square root the opposite side. And then I pull out my x. X radical 2 is c. So that means whatever my leg length is, say it's x, I'm just going to tack on a radical 2. I use that property a ton when I do woodwork. If I know that I want something to be square, if I know I want something to form a right angle, then I know if I check, and it's a 45-45, I know if I can check the two distances in between, that distance better be my leg length times radical 2. I use that all the time.
What is radical 2?
It's like 1.4.
Oh,
Yeah, 1.41, I think. Let me take a look at it. Square root of 2. Yeah, 1.41.
wow.
Okay, so now the directions are going to tell you to use a trigonometric function to find 30, 60, 90, and 45, 45. You can cross that out. Yeah, it's already crossed out in your guided notes there. It says use a trigonometric function. Nope. I want you to use a 30, 60. I want you to use a special right triangle, 30, 60, 90, or a 45, 45, 90. Obviously, here I'm going to be using a 45, 45, 90. Use a special right triangle, no decimals. We must have exact values. That means you can't just plug this in your calculator. That's a no-no. So here's what we have to do. I know that if I take my side length, my leg length of a 45, 45, what do I multiply it by to get to my hypotenuse? If you've got your leg length, what do you multiply by to get to your hypotenuse? By radical 2. So I know x times radical 2 is 20. And now we solve for x. We divide over the radical 2. Can I leave it like that? Nope, got to rationalize. We're going to be rationalizing a lot. 20 radical 2 over 2, which is 10 radical 2. Yes, sir. The memorization of the special right triangle. You just got to know that that's multiplied by radical 2. No, the side length, you have to memorize what's happening to each piece. If you want the hypotenuse is the side length multiplied by square root of 2. So if the side length is x, and I take x multiplied by the square root of 2, I get 20. And that's how I can set up that statement to solve for x. And I can do the same thing with the 30, 60, 90 triangle as well. Do I have my 30 side in this triangle?
No.
No, I want to solve for it. And you know what we're going to do? We're not only going to solve for x, but I'm actually going to tack on, we're going to solve for y as well. So what's given to me? What's given to me?
The hypotenuse.
What's the relationship between the hypotenuse and the 30 side?
2.
It's that multiplied by 2. So if I've got 74, I almost said it. If I've got 74, what's my 30 side? 37. Right, 74. And here's the reason why. If I take my 30 side and I multiply it by 2, that gets me, oops, sorry, that gets me my hypotenuse. Right? If I take my 30 side and I multiply it by just 2, that gets me my hypotenuse. So x is equal to 37. So if I know that this is 37, then what's y? 37 radical 3. Where'd the radical 3 come from? The memorization of the 30, 60, 90 right triangle. Just a special note, I know we don't have one like this on this guided notes, but if I had something like this is a 30 side and maybe this was 6, and this is x and this is y, what would I do to x to get to my 60 side? Multiply by what? Multiply by radical 3. So I could create this equation. X times radical 3 is equal to 6. Couldn't I do that same thing where I divide over the radical, just like I had in a 45-45? I just made this up. This is not anywhere in the guided notes. I just want to show you an example where you would have to divide by a radical in a 30, 60, 90, because that is a case. I do have to do that sometimes. And then I would have to rationalize to get 6 radical 3 over 3, so 2 radical 3. Now, if my 30 side was 2 radical 3, what's my hypotenuse? 4 radical 3. Don't multiply the radical, just the number on the outside. You wouldn't say 4 radical 6, you'd just say 4 radical 3. Okay. So there is a possibility. In my opinion, the hardest case out of a 30, 60, 90 triangle is when you're given the 60 side, like this. That's the hardest case. Because then you have to divide by the radical and then multiply by 2 to get your hypotenuse. Okay. Everybody take out your calculators. Your calculator is defaulted to, I think it's defaulted to radian measure. And we'll talk about what a radian is when we get to section 13.3. But let's check, let's see. Yeah, my calculator is defaulted to radian. If you click on the mode button, you want to scroll down to where there's a radian and a degree, and you want to highlight degree for right now. You don't even know what a radian measure is. So that's what I'm going to do too. I'm going to scroll down to degree. I'm going to have degree highlighted.
What is the radian?
We'll talk about that. I'll tell you when you're old.
No.
Make sure that your graphic calculator is set to interpret angle values as degrees and not radians for right now. Now, when we do that, we can answer questions, and our answers will give us back a degree measure and not a radian measure. A skateboard ramp will have a height of 12 inches, and the angle between the ramp and the ground will be 17 degrees. To the nearest inch, what will the length L of the ramp be? Whenever I'm doing a trigonometry problem, you should draw it out. Whenever you're doing a trigonometry problem, draw it out. Where's your right triangle? What do you know? Here's my skateboarder. Aaron. A wrong.
Probably didn't hear
A skateboard ramp will have a height of 12 inches. Okay, that means that this is 12. And the angle between the ramp and the ground will be 17 degrees. That's my theta. To the nearest inch, what will the length L of the ramp be? There's L. What trigonometry ratio am I going to use? Based on theta, based on 17 degrees, what are the two pieces of information that I have and I'm looking for? Opposite and hypotenuse. So I'm going to use sine. I have the opposite. I'm looking for the hypotenuse of based on that angle, right? I have the opposite. I'm looking for the hypotenuse. So I'm going to use sine. Sine of 17 is equal to the opposite side 12 over the hypotenuse L. Now, how do I know I want my calculator in degree mode? Well, look, wasn't I given an angle measure in degrees? That's the way I know I want my calculator in degree mode. Now, whenever you're solving for something on the bottom, remember that the best case scenario, or the best way to solve this is to treat it like a proportion and cross multiply. So I've got L times sine 17 is equal to 1 times 12 is 12. And then I have to divide over the sine of 17. So L in this case is going to be 12 over the sine of 17. You're going to find that basically what we need to do is just flip-flop the sine 17. Okay, you can just multiply over the L and divide by the sine 17, and you get 12 over sine 17. Now, put that in your calculator. We've got 12 divided by the sine of 17. Now give me 41.04. 41.04 inches. Well, if you wanted to do it in radian measure, you would have to convert the degree measure into radian measure, and then run that same value in radian mode, which we'll do in section 13.3. Okay, so questions about that? Again, whenever you're doing a word problem, make sure that you draw it out. If, for example, this next one, it deals with angles of elevation and angles of depression. Remember, an angle of elevation is basically from the horizon line up at something. Like if you're looking up at an airplane, the angle of elevation is the horizon line up to the airplane. If you're in the airplane looking down, that is called an angle of depression because your horizon line, whatever you're looking at, your line of sight, is below the horizon line. So that would be an angle of depression. The angle of elevation and the angle of depression are always made with the horizon, with the horizontal line. Now, what types of angles are angles of elevation and depression? The angle of elevation of one is the angle of depression of the other. What type of angles do you see here?
Right angle.
No, those are not right angles.
I mean,
Alternate interiors?
Yeah.
And if you know alternate interiors of two parallel lines, aren't they always congruent?
Yeah.
How do we know that these are always parallel? Because they're always horizon lines. So therefore, they have to be parallel. Any two horizontal lines are parallel. So therefore, since they're AIAs, you can say that, yeah, they're definitely congruent to one another. Any angle of elevation will be the same as the angle of depression of the opposite thing. So take a look here. A biologist, we'll call it Mr. Wolf, whose eye level is 6 feet above the ground. Yeah, right, he's not that tall. And measures the angle of elevation to the top of a tree to be 38.7. So let's draw it out. We've got, here's Mr. Wolf. Okay. He sees that, and his eye level is a joking 6 feet off the ground. He measures the angle of elevation to the top of a tree. Here's my tree. Thank you. It's a nice tree, isn't it? Kind of looks like an atom bomb, too, right? He measures the angle of elevation to the top of a tree to be 38.7 degrees.
How do you do that?
You could use a clinometer. It's this thing that measures angles up to the top. When I used to teach geometry, we used to make them. We used to go outside to measure things. I don't teach geometry anymore. If the biologist is standing 180 feet from the tree's base, what is the height of the tree to the nearest foot? Okay, so can't I create a right triangle here? can. I can. Let's call that x. What trig ratio will solve for x? We don't deal with the hypotenuse here, so it's not cosine or tangent. It's not cosine or sine. It's tangent. The opposite is x, the adjacent is 180. So we say the tangent of 38.7 is equal to the opposite x over the adjacent 180. No, now this is x is equal to 180 times tangent of 38.7. Because I'm solving for my numerator, so all I need to do is multiply over the 180. 180 times tangent of 38.7. That's x. So let's solve for it. 180 times tangent of 38.7. It's going to give me 144.21 to the nearest foot. 144 feet. But wait, there's more. Why? Why is there more?
The height of Mr. Wolf.
The height of Mr. Wolf, right? The joking 6 feet, right? I have to add that back on. So 150 feet. Okay. The last thing that we're going to look at is the inverse trig functions. The inverse trig functions being the reciprocal trig functions. When you have sine, cosine, and tangent, there are reciprocal trig functions. You can talk about the inverse sine, the inverse cosine, the inverse tangent. The reciprocals of sine, cosine, and tangent are ratios that are trigonometric ratios. They are trigonometric functions called cosecant, secant, and cotangent. They've got special names to them. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. I will say this. It's easy to identify what the reciprocal of tangent is. It's just cotangent. It's got co in front of it, right? That's easy. What's harder is to identify what goes with what in terms of secant and cosecant. I always remember it this way, and I don't know why this stuck in my head. The cos don't go together when you're talking about secant, cosecant, cosine, and sine. So cosine does not go with cosecant. Cosine goes with secant. Sine goes with cosecant. Okay? And what does that mean? That means, look, if sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite. If secant is, if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. If tangent is opposite over adjacent, then cotangent is adjacent over opposite. Okay, there are 3 new trigonometric ratios, but they're not really new. They're just the reciprocals. Okay, they're just the reciprocals. Okay, so let's take a look and identify them. Find the values of the 6. Yes, 6 trigonometric ratios for theta. Now, what's weird about this one? Like if I go to calculate my sine of theta, and I'm going to start a list down here. If I go to calculate my sine of theta, what is sine theta? 10 over 26, right? Reduce it down 5/13. Y'all follow me there? That's an easy one. When I go to calculate cosine theta, what would you say? Well, what's my adjacent side? It's not there. Can I find it? Yeah. Isn't it a right triangle? Let's use Pythagorean. Let's call that A. A squared plus 10 squared is equal to 26 squared. Ooh, 26 squared, I don't know that one. Okay. 676. So A squared is 576. So let's see. Hopefully that's a nice even square root. Let's check. Let's hope. Let's go. 24. Now, sometimes that will not come out to be a nice even square root. And then when you go to calculate the trig ratios, you're going to have to do some little bit of a manipulation there. So that's 24. So that means cosine is 24 over 26, or 12/13. And tangent of theta is going to be 10 over 24, or 5/7. That should have been easy. That should have been very similar to the very first problem that we did. What's different now is now we're going to take the reciprocals. Now, what goes with sine? What's the reciprocal of sine? Cosecant, abbreviated CSC. Cosecant theta is going to be the reciprocal. I don't need to go back through and look. It's just 13/5. Right? It's just the reciprocal of sine. If I wanted the secant value, that's just the reciprocal of cosine. 13/12.
How'd you get 5/7 from 10/24?
12, 5/12.
Whoa, why did I get 7? Where'd that come from? That's weird. Okay, 13/12. And then cotangent of theta is 12/15, or 12/5. Whoa, I almost screwed that up again. So you can use the 3 trig ratios to just find the reciprocals of them to find the other 3 trig ratios. 3 of them are your sine, cosine, and tangent. The other 3 are the reciprocal values. Okay. Now, how do we use those? We're just getting the tip of the iceberg here. Okay. So excited for the rest of this chapter. It's gonna be so great. I love trigonometry. I haven't taught this in so long. All right.